Understanding polarity is fundamental to understanding the field of chemistry, whether that be biochemistry, organic chemistry, or in the case of my research, analytical chemistry. Let's dive in and understand what exactly polarity is. On the left side of the screen, you'll notice there is a water molecule, H2O, and towards the top there's a red cloud with a delta and a minus. That means this region is partially negative because it has higher electron density there. Electrons are negatively charged atomic particles, and when they have higher concentrations in certain regions, it makes a more negative charge. Towards the bottom blue region by the hydrogens, you'll notice there is a delta and a plus. That means this region has a partial positive charge or less electrons. When a molecule has differing charges in it, it is considered a polar molecule, and each of those charges is considered one of the poles. Just like how some molecules have a positive pole and a negative pole, magnets have a north pole and a south pole. If you've ever played with a magnet, you may have noticed that the north pole and the south pole are attracted to each other. However, if you flip the magnet so that the south poles are aligned and the north poles are aligned, you may have noticed that they are very hard to push together because they are repelling. Similarly, molecules that have opposite charged aligned will be attracted to each other, and the similar charges will repel. In this example of a water molecule, the partially positive and partially negative regions are opposite charges and will therefore attract, where the same charges will repel. Here's a list of common polar molecules. We already discussed water in the middle. On the left, there's isopropyl alcohol, which is a common disinfectant. Ammonia is also a common disinfectant, and methanol and sulfuric acid are reagents we use in the chemistry laboratory. Opposed to polar molecules, nonpolar molecules will have little to no charge difference between their atoms, or they could have symmetry. They will also usually contain carbon. Here are some common nonpolar molecules. The first one on the top left is octane. That is found in gasoline. On the right, you have ibuprofen, which is a medication you take for pain and inflammation. And on the bottom, there's stearic acid, which is soap. Nonpolar and polar molecules, like oil and water, do not mix very well. You may have noticed this before if you poured oil into a glass of water, or if you've seen images of the Deepwater Horizon oil spill in the Gulf of Mexico. Fortunately for remediation crews, oil and water have opposite polarities and therefore do not mix, and they were able to skim the oil off the surface of the ocean. Previously, I said that polar and nonpolar molecules do not mix, but then also said that soap is a nonpolar molecule. But we all know that soap and water do in fact mix. So how can this be the case? If you look at the stearic acid molecule on the right, you'll notice there's a pair of red oxygens on the far side. This gives the stearic acid enough polar characteristic to be miscible or able to mix with water, while still having this long hydrocarbon chain that gives it a nonpolar quality. So it is more accurate to say that molecules have a gradation of polarities where they can be classified as more polar or more nonpolar rather than one or the other. We use these subtle differences in polarity in chemistry to separate molecules out of complex mixtures. On the bottom left, there is a picture of a fractional distillation column at an oil refinery where oil is separated into its base petroleum products. On the right, there's a picture of me performing a column chromatography experiment of an egg yolk. You'll notice there is a white solid in the column. This is silica gel, which is a polar molecule. When the egg yolk sample is added, the polar molecules will be more attracted to the silica gel and thus retained in the matrix, where nonpolar molecules will travel through more quickly and come out to be collected at the end. This principle of separating by polarity has applications in other analytical chemistry equipment, such as this high-performance liquid chromatography machine. You don't need to get caught up in the details of this diagram, but what is important is number 9 in the middle. This is a column that will be packed with either polar beads or nonpolar beads. If it is packed with polar beads, then polar samples will be retained more than nonpolar samples. So the nonpolar samples will come through faster, and we have effectively separated them from the mixture. In my research, I use a high-performance liquid chromatography column to separate amino acids out from eggshell samples. Amino acids are the building blocks of proteins and are found in all biological systems. They also have varying side chains that have different polarities. So I can use this nonpolar chromatography column to separate out the amino acids from an eggshell protein matrix sample. Thank you for watching this video. I hope after this presentation you better understand the concept of polarity and its importance in the field of chemistry.